Hello and welcome to Algebra 2 with Mr. Clausen. Today we are going to talk about multiplying and dividing radical expressions. So to get started, we will look at how we can multiply radical expressions, some of the rules that apply to multiplication, as well as dividing radical expressions. And then I'm going to finish off the lesson talking a little bit about how to rationalize the denominator of a radical expression, because that's an important skill that we'll need to know as we move forward with radical expressions. So to get started, I just want to break down some radical expressions, how we multiply them or simplify them out. So one of the things that we need to do in algebra is sometimes take a more complicated, unsimplified expression such as the square root of 50x to the fifth and simplify it completely. Now, unlike the previous video, this one will include examples where things are not perfect squares or perfect cubes or those type of situations. So, for example, 50x to the fifth squared, and we need to simplify, assuming that all variables are positive, we can split this up accordingly. So if we use prime factorization, we can say 5 and 10 and 5 and 2, and we can see that there are a pair of 5s here in 50. And again, remember that a square root has an index of 2, so we can look at a situation like x to the fifth and know that there's at least 2x squareds present, but there is still one extra x remaining. So there would be an x squared, 2 of them, that could be pulled out, and then these could be brought forward in front of a expression like this. Another way, like we demonstrated in the video, is we could look at it from a perspective of, you have 5 squared times x squared times 2x, all under the radical sign here. Okay, and again, you don't need to do this. I'm just showing you that we have these pairs present. We can pull them out front, and we can simplify this quickly by saying 5x squared times the square root of 2x. And that would be the final simplified answer in terms of this given expression. Now let's talk about where we actually have multiplication, because this is an important concept as well. Now, one of the things is as long as your indexes match two given radical expressions that you have, these values are commutative. So what that means is that we can take two separate cube root values and we can put them together under the same tree here. And we can multiply them together if we want and get a situation where we have negative 729 as our value. But again, keep in mind that this is a cube root, and we want to be able to factor this out if possible and find what that is. So if you use your calculator, you could and hope that it's a cube root, but if it's not, we can still use the same technique that we did before. So if we look at it this way, we're trying to find a cube. We can pull out negative 81. We can pull out a 9. And actually, I'm just going to pick these because I already had them there. And then we can pull out negative 9 and 9. And actually, we have to have 3 the same thing. But the thing is if we have negative 729, we could pull negative 9 out 3 times. And we would have a cube value. And one of the things that I want to point out here is that you can have a negative radical expression if the index is an odd number. So if it's like 3 or 5, you can totally have odd values because you can multiply 3 odd numbers together and get a negative number. So in this case, this specific value would equal negative 9. Okay, so with that example in place, let's look at this last example here. Okay, so for multiplying expressions, just like the previous one, the indexes match, so we just want to combine them together. So if we go and we just say, for example, 294 is what the product of 7 times 42 will be. And then if we go x times x to the fifth, that'll equal x to the sixth. And if we go y to the ninth all by itself. That'll be y to the ninth. And actually, let's just bring this out, tab it down, and we'll know that this whole thing's enclosed here. And one of the things I want to point out here is that if we have this situation, we want to split out the primes again, or we want to find the specific things that we can pull out in order to simplify this. And sometimes it's just easiest to combine it first and then figure out what's possible, because it might be a root from each of these that are kind of combined to what we need. So for example, you could split this part previously and look at it and go, oh, there's 6 and there's 2 7s. So I could say, you know, there's 2 7s. I'm interested in things that are squared mainly because I know I have a square root here. And let's see, I have 3 pairs of x squareds here. So we can multiply this by, let's see, x cubed squared, because there's 3 pairs. There's 4 pairs of y's. So we can say y to the 4th squared. But there is 1 extra 6, and there is 1 extra y. So we'll include all those as well. And again, I'm just trying to find all the individual parts. There's a couple different techniques that you can use. You can prime factorize the whole thing. But, you know, the idea is that if you have these pairs, we want to pull all these out front, and we want to simplify it completely by saying 7x to the 3rd, y to the 4th, and then have the remaining part that's still under the radical there at 6y. And that would be your solution for this given circumstance. So those are some examples of multiplying radical expressions. Let's talk about an example by dividing radical expressions. So if you want to divide a radical expression, one of the things that is worth keeping in mind is that these are also commutative. So as long as the index between these radical expressions are the same, one of the ways that we can rewrite this, and that you'll want to take advantage of, is you can rewrite these 2 individual square root expressions into one big one where the whole thing is present underneath one radical sign. And again, the reason that you may want to do this is that if we're looking at an expression like this, we can simplify some of these harder examples. So for example, I see that the x here gets canceled out and the 3 can turn into a 2 here. And if I'm thinking about 48, I know that 3 goes into 48 to some multiples. So for example, 48, if I go 16 times 3, yeah, the multiples of 48 are 3 and 16. So I can cross out 3, I can cross out 48 and replace it with 16. So what that allows me to do is I can take 2 individual square root values that were a little bit more difficult to deal with, and I can simplify it into this 16x squared over y squared format. And I can actually go as far as undoing this commutative process that I did if I want, if that makes me feel a little better, as I can say 16x squared and divide it by y squared, the square root of y squared, and get 4x all over y, and get this nice divided out radical expression. Okay, so something to just keep in mind, a property that is present for all radical expressions. So let's look at one last skill that we need to talk about a little bit, and that's this idea of rationalizing the denominator. So one of the things I want to point out is I can take a expression like this, I can try to simplify it out, and you know, if I put everything underneath one radical, it doesn't really make any difference here. It really, the only thing I can do is I can go to the square root of 5 all over 2 square roots of 2x. That's the best that I can do. And one of the things that I want to point out here is that whenever we have this situation, mathematicians do not like having these irrational numbers in the denominator, because irrational numbers have infinite decimals. And the thing is if you're dividing something and a denominator, it needs to have a fixed value technically. So one of the things that we do to overcome that issue is we rationalize the denominator. Well, the easiest way to rationalize the denominator is to multiply it by 1. And you might be like, well, what's the value of doing that? Well, you have to be tricky about how you multiply it by 1. So one of the things that is typically done is if you want to rationalize the denominator, you multiply it by the square root of the remaining part that you want to rationalize in the denominator, in the numerator, and again in the denominator. And the idea here is that this little tidbit that I added is equal to 1. It's just a 1-to-1 ratio. And so by multiplying this original radical expression by this new radical expression, I'm not changing the actual expression. I'm just using 1 as a multiple as a way to make this a little cleaner. Now, don't cancel these out. That's not what we're trying to do. What we are trying to do is we're trying to pair these guys up right here. So that way, when we multiply the square root of 2x by the square root of 2x, we get this new expression where we have the square root of 5 times the square root of 2x on top. And then on the bottom, we get 2 times the square root of 2x squared. And again, what that allows us to do is we get the square root of 5 times the square root of 2x, again, just for the sake of explaining this, where we get 2 times 2x. See how that works? So now we got rid of the square root radical in the denominator, and now we can just combine the common part on top that shares the same index, and we can say 10x, the square root of 10x, all over 4x. And now we have a completely simplified radical function with a rationalized denominator. And now let's look at one other example here, because this is an example that I find a lot of students get tripped up on, is an example like this. This is really simplified as far as we can possibly go, but we need to rationalize the denominator. And the reason this trips students up a lot of times is now we have this cube root example here. And with cube roots, remember, you have to multiply that root 3 times. So what I'm going to do here is I'm going to do something very similar to what I did before, but since it's a cube root, I'm going to go the cube root of 2 times the cube root of 2 times, okay? Because I need 3 cube roots of 2 to turn this into a 2. And I'm going to do the same thing up here. I'm going to go the cube root of 2 times the cube root of 2. Because again, I'm not trying to change the radical expression. I am just trying to multiply it by 1, or a factor of 1, so that I can clean up this ugly denominator that mathematicians don't generally like. Because now, what I have, if I combine all these together, I have the situation now where I have the cube root of 2, and I have that to the 3rd power. And then on top, I have the cube root of x times the cube root of 2 times 2. And now I'm adding more on top here, but the thing is on the bottom, I can clean that up to a 2. I get the cube root of x times the cube root of 4. These guys share the same index. So now I can rewrite this whole thing as the cube root of 4x all over 2. And I now have a cubic radical expression completely simplified with a rationalized denominator. So with that said, that's all I have to show you in this video. I hope you have a better understanding of radical expressions, how to multiply, divide them, and rationalize their denominators. And with that said, let's do some math.